Hello, my name is Nandi Shabazz, and today I will be showing how the monotonic sequence theorem can apply to the given sequence 1 over 1 plus 1 over square root of a sub n. And we were given that the first term of this sequence is equal to 1. So the monotonic sequence theorem states that if I have a sequence that is bounded and monotonic, then it converges. And in short terms, or what that really means, is that if I have a sequence that is only increasing and has an upper bound, or only decreasing and has a lower bound, the sequence will approach some limit. So what I'd like to do today is show how the given sequence is both monotonic and bounded, and then use that to find the limit. So the first thing that I'd like to start off by showing or working on is the monotonic aspect of it. I'll start off by showing finding the first four terms of the sequence, and then using induction to prove that for the remainder terms of my sequence. So the first term that they gave me was a1, which is equaling 1. Now this is a recursive formula, so in order for me to find my next term, I'm going to go ahead and let n equal 2, or n equal 1, to help me find a2. So when I substitute n equal 1 into my formula, I get that 1 over 1 plus 1 over root a sub 1, which we know is 1. So I'm going to go ahead and substitute that into my sequence. If I plug this into a calculator and simplify, my denominator is going to be 2. And if I do the remaining division, that's going to give me 0.5. So I can use this 0.5 now to help me find the third term of my sequence by letting n equal 2. If I let 2 plus 1 will give me my third term of my sequence. So I have 1 plus 1 over the square root of a2, which I know that to be 0.5. So I'm going to take the square root of 0.5 in my denominator, plug all of that into a calculator, and I get 2.24142. I can further simplify that to give me 0.4142. I don't know, I can see that I go from 1 to 0.5 to 0.4, so it seems like this function is decreasing. But let's go ahead and find the fourth term of my sequence to really see what's happening. So I'm going to let n equal 3. 3 plus 1 will give me my fourth term. So I have 1 over 1 plus 1 over the square root of a3. .4142. I plug that into a calculator, give me 2.5538, which will simplify down to 0.3916. Okay, so I see that this function my series does seem to be decreasing. So what I can say, or let's assume, that my next term, a sub n plus 1, will be less than my original a sub n for some n greater than 1. I want to show, though, that this works for every preceding term. So a plus 2, or n plus 2, will be less than its previous term, a sub n plus 1. Now, by my recursive formula, the sequence will look like a sub n plus 2 1 over 1 plus 1 over the square root of my previous term, so it'd be n plus 1, where my previous term would look like a of n plus 1, 1 over a sub n. Now, the given function (1 over 1 plus 1 over the square root of x) is decreasing. When x is greater than 0. And the reason why it's decreasing is for a couple of reasons. A couple of things are happening. If I were to take the derivative of this function, the values of that are decreasing. I notice also here that I am taking the square root of a number and dividing all of that, so it's only going to get smaller and smaller and smaller and smaller. So by using my inductive hypothesis, where I originally said that a sub n plus 1 is less than a sub n, I can conclude that the preceding term, the next term, a sub n plus 2, behaves the same exact way. Oops. As the term that preceded that, n plus 1, which is smaller than the term that preceded that. So because all of these are decreasing, 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 I could say that my function as I continue on, or my sequence as I continue on, decreases. A sub n is decreasing. So my sequence is monotonic in the fact that it is only decreasing. So now I'd like to speak to its boundness. I'm going to rewrite my sequence again. Okay, so we just saw that it was monotonic in its decreasing form. So since it's decreasing, it needs a lower bound. So let's talk about the boundness. Now, I'd like to say that because I'm taking square roots, so I'm taking square root, right, now that a sub n, and I'm only adding positive numbers, right, 1 plus blah, blah, blah. I know that all of the terms of my sequence will be positive. Okay, so because that's going to be positive, all my numbers are positive, 0 has to be my lower bound. Okay, so it's monotonic, it's decreasing, it has a lower bound of 0, so therefore I can go ahead, it should have some limit that I can find. So in order for me to find the limit, I'm going to let L be the limit. As n approaches infinity, my sequence is going to approach some limit. And in order for me to find that, I'm going to set my L equal to my recursive formula. 1 over 1 plus 1 over root L. And in order for me to find the value of my limit, I need to solve for L. So I'm going to first try to get rid of everything in my denominator by multiplying it on both sides. So let's see, 1 plus 1 over root L, 1 plus 1 over root L. Those cancel out. I'm left with L times 1 plus 1 over root L is equal to 1. Let's go ahead and distribute the L to give me something like L plus root L, right? If I wanted to rationalize the denominator in the same step. Now I see here that I've got L plus root L's, and when I'm solving for equations, sometimes it's just easier to think about X. So I'm going to let X equal square root of L. But that takes care of one term. So if I were to square both sides, I can have a value of X squared equaling my plane limit, which takes care of both terms in my equation. So my new equation will now look something like X squared plus X is equal to 1, which looks more like a quadratic equation if I subtract 1 on both sides. But I can't necessarily factor, so I'm going to go ahead and use the quadratic formula where A and B equal 1, but C is equal to -1. So let's see, I'm running out of room. I'm going to come up here. I'm going to have that L is equal to, or X is equal to, square root of -1 plus or minus the square root of 1 squared minus 4 times 1 times -1 all over 2 times 1. I can simplify this to give me -1 plus or minus 1 plus 4 over 2, which further simplifies to the square root of 5. Now, because X needs to be positive, I can only have one solution, which is plus root 5. I can negate the negative. But if you recall, my X doesn't necessarily gives me my limit. It gives me the square root, or the square of my limit. If I square my X, square both sides, that should give me my actual limit. So let's square this and square this. And I can have that my limit, my X squared, will equal 3 minus root 5 over 2, which is the limit of my sequence. Thank you for listening.